Hello everyone, thank you for joining us for today's webinar. Today we are going to be looking at how Raman Spectroscopy can help with research into green energy. I'm Ian Hayward, your Renishaw host for today. With me are Tim Batten, our Platform Product Manager from the United Kingdom, and Tim Smith, Raman Applications Manager, also from the UK. We're recording today's webinar and will make the recording available to you later. We have a lot of you in the audience, so I've muted your microphones to prevent confusion. But please ask questions whenever you like using the chat window on the right hand side of the screen. We'll be answering your questions towards the end of the webinar. I'd now like to hand over to our presenters, Tim Batten and Tim Smith, starting with Tim Smith.
Thanks, Ian, and welcome everybody to this Renishaw webinar. We're going to be talking about Raman Spectroscopy as a tool for green energy research. In this webinar, we are going to be discussing some of the existing and new technologies supporting batteries, solar cells, and energy storage. We will give an outline of the Raman technique and the key information produced, both looking at chemical information and material properties such as strain and crystallinity. To best support this work, we'll also outline some of the key Raman system capabilities and performance areas. We'll then show how the Envia Raman microscope can help us in understanding and developing these areas through 3 detailed case studies. Case study 1 is going to concentrate on the analysis of lithium-ion battery electrodes and operando measurements. In case study 2, we're going to look at the combined photocurrent and Raman analysis of silicon solar cells. And in case study 3, we're going to look at the correlative analysis of perovskite materials and modules. And then we're going to conclude at the end. We all know that green energy is a vital research area. And over the last 2 decades, there's been a lot of advancement in renewable electricity production, battery technology, that's led to these technologies being included in everyday appliances. There's obviously a continual need to develop these further as energy needs increase, but also as net zero emission targets become more and more commonplace. And there are certainly some very ambitious targets for the removal of fossil fuel based products, such as diesel and petrol vehicles, and even gas powered boilers. And of course, these are driven by environmental concerns, but also economic and regulatory areas. And this is very much driven by the International Energy Agency, the IEA, who recently targeted the energy sector as accounting for about 75% of the emissions of the greenhouse gases that are contributing to our increasing global temperatures. So it's never been more necessary than now to help understand and develop these technologies. So we're going to show data on lithium-ion batteries. So these are rechargeable batteries, where lithium ions move from a negative electrode through an electrolyte to the positive electrode, the cathode, during discharge. And these batteries use an intercalated lithium compound for the cathode and carbon material, typically graphite, as the anode. Optimizing the efficiency and the longevity of this kind of technology is crucial. Being able to better understand these processes and optimize them is important for the future. We're going to take a look at solar cells. So these are devices that convert the energy of light directly into electricity. And this renewable energy is going to be so important for the future. And again, understanding and developing these cells, making sure that we can extend their lifetime for as long as possible, are going to be key to help us displace fossil fuels. Finally, we're going to look at perovskite cells. So these are cells that have a perovskite structured compound, usually a hybrid organic-inorganic lead or tin halide material. And these are probably the fastest growing solar technology, with efficiencies increasing from around 4% about 10 years ago, now being able to get up to around 25%. In general, these cells have low production costs, and so they're commercially very attractive. And Raman spectroscopy will play an important role in helping develop these cells. So what is Raman scattering? Well, we start off with our material. We then use a low power laser that we illuminate onto the surface of the material. This laser light interacts with the surface and produces a whole range of different light coming back. Some of this is reflected, some is transmitted, and of course some is scattered. Most of the scattered light is of the same laser wavelength, whereas a small amount of that light, about 1 part in 10 million, has a change in colour, so therefore a change in energy. And this is the Raman scattered light that tells us information about the material chemistry and the material properties. The Raman scattered light is diffracted into its individual wavelength elements, and then this gives rise to the Raman spectrum that tells us about the material. So here we see a Raman spectrum of diamond-like carbon that's often used to form protective layers. So what's the information that we get from these Raman spectra? Well, the characteristic frequencies where the Raman bands are located tell us about the vibrations in those materials, and these are highly specific to certain types of materials. So we can identify materials really easily, and of course we can also compare materials to understand if they're the same or different to other materials. The intensity of the Raman band correlates to the amount of material, so concentration. And so we can use the technique in a quantitative way to understand how much of something might be present. We can make use of the polarization of the laser to understand different crystallographic orientations. And then these two bottom ones are really important. We can understand the crystallinity of materials. As the Raman band becomes more broad, we've got more different environments of the structure being analysed. So typically this means that we're looking at less crystalline materials as things become more amorphous. And then the band position tells us about any stress or strain that might be present as that local bonding environment is being perturbed. So there's a whole wealth of information from just a single Raman spectrum that we can get. Raman analysis can be performed at single positions on materials. So here we've got a highly focused laser spot at around about 1 micron or smaller, and this can be targeted to analyze, of course, very small areas on our sample. Here we're looking at rhenium disulfide, where we can see some optical contrast, and then we can understand how this correlates to the number of layers of rhenium disulfide that are present at those points. And we get a Raman spectrum at each one of those positions. We can go a step further than that. We can produce chemical images. So this is where we have a Raman spectrum per pixel in these images we see. So we can build up pictures that represent either the chemistry or properties of materials. So here we've got the peak intensity. That's given us information about orientations of grains within poly-crystalline silicon solar cells. We can look at the peak position to understand what kind of stress or strain might be present over that same area, particularly where we have interfaces between some of those different grains. And we can look at the change in crystallinity across that area as well. So from one set of mapping measurements, we can get a range of different information back. We can also look at volume maps as well. So here we've got a patterned gallium nitride structure. You can see we've actually got a volume, and we can move the slice that we're looking at through the Z-plane to see all the different features that are present. So this is essentially a series of 2D images combined together into a single volume. We can also overlay 2D images on 3D surfaces, and typically these 3D surfaces are from topography. Here we have a Raman image showing graphene superimposed on the uneven copper topographical surface. But we can also show the 3D surface based on the property information or information from other techniques. And so we have a range of products that we can use to get this information. In the case studies, we're going to be talking about the Envia Raman microscope in the center here. This is a research grade Raman microscope, has all the performance characteristics we need to perform this type of research. We have benchtop systems that allow us to perform work in production environments and where research microscopes might not have the same accessibility. And then in the bottom right here, we have Versa. Versa is a remote probe based system, and this brings portability along with high-end Raman analysis. So the Envia Raman microscope has all the performance and operation requirements needed for the type of work we're going to be talking about in these case studies. It's simple to operate with a high degree of automation, whether it's looking at your sample, whether it's changing from one configuration on one laser to another laser, or checking the performance is optimized for our needs. It's by design high throughput and highly sensitive, and this makes it especially well suited for the performance of Raman mapping measurements, where we need to get lots of Raman data in a short space of time. The high spectral resolution performance provides excellent specificity to a range of materials and even similar materials such as polymorphic forms. This is also important when looking at small shifts in the Raman spectrum and performing stress and strain measurements, where changes of 100th of a wave number in position can be detected. And at the sample, the laser is diffraction limited in terms of the spot size on your sample. This allows us to get very high spatial resolution work performed. And of course, if we want to get larger averages, then we can do this too. One of our more recent advances, live track autofocus, gives us the opportunity to be able to maintain focus of a sample as we're collecting our Raman data. We're also able to produce topographic images of a surface of a material. And of course, we can then layer a chemical image or a property image on top of that 3D surface. So it's a very capable system, suitable for even the most challenging types of measurements we want to perform. So having all this Raman data is great, but we understand that there are many other techniques that we need to be able to fully understand the different materials and devices that we're interested in. So we support the ability to do correlative work, enabling the incorporation of images from other methods into the Wire software platform, where we can perform further work or directly correlate that information together. So the live track method I mentioned previously, this adjusts the sample position to allow us to be able to track that sample during data collection. And this happens continually as we collect data in real time and benefits not only the Raman data and the optical browsing, so we don't need to adjust manually any of the focus, but we get the topographic information and we can support the analysis of dynamic systems which need to be held in focus and that may otherwise move during data collection. So now I'm going to pass over to Tim Batten, who's going to take you through the case studies.
Thanks, Tim. I'm going to begin by talking about a few case studies. The first case study focuses on lithium-ion batteries. What can Raman tell us about lithium-ion batteries? So there are a few things they can do that are really useful. The first thing is it can identify the components in the battery. So that can be carbon materials, identifying the different allotropes, which is something which Raman excels at and is quite difficult with other techniques. Being able to identify metal oxides, not just the elemental composition, but also the relative oxygen composition. Polymers, binders, electrolytes, and ionic liquids. So it really is a great tool for understanding what materials you have in your batteries. You can also characterize structural properties such as strain and crystallinity, and you can correlate the composition and structure with performance. This is a great way to understand if you're designing these batteries or making electrodes from mixtures. You can then try and work out what's going on with your battery, which is giving it better or worse performance. The other thing we can do, is shown on the image on the right, is study the distribution of components on the electrode surface or in cross section. So here I've got a cross section example. You can see that I have an optical image, and overlaid on the optical image I have a Raman image, which is predominantly green. I've coloured this image based on the composition of the materials in the electrode. So green regions correspond to graphite, blue regions correspond to acetyl black, red regions correspond to styrene butadiene rubber, which is a binder in these particular electrodes. So immediately we've got a very nice way to look at composition of the electrodes and the relative fractions of the different components. One other really interesting thing we can do is we can take this a stage further and look at structural changes in batteries due to operation. So that might be changes in strain or crystallinity, or it might be changes in composition or distribution all together so we can understand what's going on as we charge and discharge our battery over time. My first example is looking at lithium-ion batteries, and in this case looking at the anodes, which are typically made of carbon materials. The image on the left shows an anode, and this is a very typical anode. And one of the challenges with this sort of material is that the surface is very rough. So if you look at the image on the left, you can see we've got regions where you can clearly see the grains of the anode are in focus, and you've got regions very close by that are out of focus. And unfortunately, this roughness occurs on quite small length scales. And this is a very challenging sample for Raman spectroscopy, because if we now try and map this region, we'll have regions which are in and out of focus. To make any sort of corrections on these length scales is very laborious, and ultimately means that you would normally have to do the mapping measurements manually. Now, this is the sort of sample where our live track technology really shines, because we can set live track map on this sample, and the stage will move to keep the sample in focus over the whole mapping region. So we've just taken that laborious manual focus out of the equation, and we're able to quickly and easily map this, ensuring the surface is in focus at all times so we get the best quality Raman data. Not only that, but we get the topography information, and this is what's shown on the image on the right. So you can see here the change in height in microns. So we're seeing about 30 micron change in height of the sample, and we can see the actual structure of the material. So if you look at these two images, for instance, you can see this blue hole. It is the out of focus region on the optical image. You can also see where we've got the grains nicely in focus. They tend to be a bit more greeny in colour, like in the bottom right of the image. So what we've got here is not only a tool which lets us investigate the chemical properties of the material, but also one which produces a topographic information from the surface. And that's going to be important for this example, as you'll see in a couple of slides' time. So I mentioned this was a battery anode, and I mentioned that it was made from different carbon materials. With Raman spectroscopy, we're really excellent at identifying different carbon allotropes. We're quickly able to determine that this particular electrode is composed of natural graphite and carbon black. And you can see the spectra here are very different, so it's very easy for us to differentiate between the two materials. Now we can go back to our Raman image, and we can look at each of the points in the Raman image and determine whether or not they're natural graphite or carbon black. And in this case, we've got this image on the right, so you can see red and yellow, same color scale. And from this, and using our fraction estimate tool, we can basically say that this electrode region is about 25% natural graphite and about 75% carbon black. So now we can combine the two information, so the topography with the distribution of the carbon materials as identified by Raman. In red here we have the distribution of the natural graphite overlaid with the topography image, and in yellow we have the distribution of the carbon black overlaid with the topography image. And there are a couple of things we can draw together from this combined information. So the first thing is that we tend to have natural graphite at the top of the topography features, so the peaks, and we tend to have carbon black in the valleys between these features. This is a very interesting thing because it's a very easy to comprehend, and that's basically our natural graphite particles tend to be much larger than the carbon black particles, so they tend to stick out from the electrode. And when the carbon black is actually added to the mixture, it infills between these particles, creating like a matrix with them embedded in. So we've been able to determine for this sample the distribution of natural graphite and carbon black, and get an understanding of why this is the case, all from one very simple mapping measurement. My next example is investigating a pressed silicon electrode. Silicon is a promising alternative electrode material in lithium-ion batteries. During lithiation, however, silicon undergoes a large volume increase, and this can lead to the creation and propagation of defects that can overall affect the performance of the device. While I've been talking, you can see on the right hand side a live track topography image of the surface of the pressed electrode, so you can see it's inherently rough. This was a relatively quick measurement covering 90 microns by 60 microns with more than 5,000 acquisitions in around 25 minutes. I'm going to show you the Raman data for this on the next slide. So here's the Raman image from the sample. I've coloured it using a few different parameters. So white regions correspond to crystalline silicon, black regions correspond to amorphous silicon. As you see, the in between the grey regions, these regions are basically multi-crystalline silicon regions. The red regions correspond to areas where no silicon is present, so we can basically see a high presence of metal in these regions. And the nice thing about this is we basically have the distribution of the materials in the electrode. With multiple cycles, we can then go back and look and see how the silicon has changed over time. Obviously, the expectation is that we'll have a breakdown in the material and we'll see a larger amorphous fraction. Lastly, I'd like to talk a little bit about in situ electrochemical characterization. We have the ability to collect Raman data from a wide range of sample changes in electrochemical cells. We're able to put samples in inert glove boxes, so you're able to measure lithium without seeing any oxidation. Our wire software provides the ability to trigger Raman collection from external devices such as potentiostats, enabling automated in situ and operando measurements. Here in these pictures you can see a picture of someone working at an argon glove box looking at lithium-ion batteries, and beneath that we've got a picture of an electrochemical cell used for this sort of analysis. To demonstrate this in action, I have some example data provided by Professor Kim at Shinshu University in Japan. Here they conducted operando studies of a graphite anode in a lithium-ion battery. They took Raman spectra at different potentials and looked at not only the Raman spectra but also the anode's appearance. They were able to show that as they changed the potential, the anode's appearance and structure change. So I'll quickly talk you through the Raman spectra on the right hand side. At high voltages we can see we basically have a spectrum which corresponds to graphite. When we drop down to 0.15 volts we see an upshift in the graphite, and this is a result of intercalation of the lithium causing strain in the graphite material, and that causes the G-band to upshift. At 0.075 volts the bulk of the electrode is still under strain, but some areas are strain free because you can see the band is shifted downwards again, so we've got this nice doublet. These strain free areas indicate basically damage to the electrode material, so we've basically permanently degraded the electrode at this potential level. You can see as we keep lowering the potentials the effect is compounded, and what was graphite slowly becomes destroyed and loses its crystalline structure, and as a result it becomes basically amorphous carbon. So at these lower potentials we can see the degradation continue and we get amorphous carbon spectra. And this piece of work's nice because basically it's done on live electrodes. This is really interesting if you're actually interested in not what your battery can do but how long it can survive under different potentials and different cycle times. So to summarize this case study, Raman spectroscopy is a really powerful tool for understanding batteries. Here we've identified and investigated battery components and the distributions. We've characterized the electrodes, taking advantage of live track to image what are inherently rough surfaces and very challenging Raman samples. We've also demonstrated how Renishaw Raman systems can be used to conduct in situ or operando measurements on batteries. My second green energy case study involves using induced photocurrent and Raman to analyze single crystalline silicon solar cell modules. I'd like to begin by giving a brief introduction to photocurrent mapping. When light is shone on an electronic device, photocurrent can be induced, and the induced photocurrent value provides information on the electronic, optical and charge transport properties of the materials in the device. Now interestingly, when we collect a Raman map, we raster a laser across the sample surface to get the Raman data, and this also creates a photocurrent in the device. By combining these two measurements, i.e. collecting the Raman data and also connecting the device and measuring the change in current, it allows us to look at these variations in photocurrent and understand what's going on based on the material properties determined via Raman spectroscopy. This is particularly relevant to research on photovoltaics or perovskites or 2D materials. In this work, solar cell modules were investigated, and that was because they were exhibiting lower than expected performance. These were PERC type solar cells. PERC stands for passivated emitter and rear contact. These are the standard high performance, high efficiency solar cells from silicon that you'll see everywhere. These are complete modules and they have a relatively complicated structure. So from the bottom up, they have a clear UV and hydrolysized stabled PET backsheet. Then you have a bottom encapsulation layer of EVA, ethylene vinyl acetate. You have bottom ribbons. You have a single crystalline silicon solar cell, then top ribbons. Then it's a double encapsulation layer of EVA, followed by a flat, non-textured iron glass. These modules were tabbed and electrodes were accessible for electronic measurements. And these samples were provided by Hubert Seigneur and Parag Banerjee at the University of Central Florida. You can get an idea of the size of these modules from the picture, so you can see them in my hand. I now want to show you some data from these modules. First of all, we conducted Raman imaging across the modules. Here we're just focused on looking at the silicon band, and we're looking at its relative position and its width. Its position is an indicator of local strain in the solar cell, and its width is an indicator of the silicon quality. What you can see here is there is some variation across the cells. I should first explain that in these images, the red region is the contact pads. In our software, we're able to mask out regions which are not of interest for analysis. So here, basically, I picked any region which didn't have a silicon spectra and I masked it off, and this removes it from the analysis. What you can see if we look at these modules, so if we look at the peak position image first, you can see running along the edge of the contact pads, we see a change in the local strain of the material. We can also see an increase in peak width as we go to the edge of the material as well. And again, this is an indicator that something's going on near the contact region. But does it matter? Is this the root cause of the performance loss? And the answer is, with only this information, it's very hard to tell. So we went on and we did some photocurrent measurements of these cells. So this is the photocurrent data. This image shows the induced current in microamps as we scanned across the device and did a Raman map. You've got this rather psychedelic image where we see quite a big variation in the photocurrent depending on where we are. There are a couple of things which are quite important from this image that we can resolve immediately. So we're typically seeing a reduction of the photocurrent near the contact pad. So here I've marked the contact pads with these blue dotted lines on the first two lines of contacts, but afterwards I've left them free so you can get an idea where they are. So we see a reduction in photocurrent near the contacts as shown by these dark regions. This typically extends around 200 microns either side of the contact pad. However, it occasionally extends further. So you can see I've drawn a square in white, which shows an area where this region extends outwards across into the gap between contacts. Here we have the Raman data from the same region, and this shows the variation of the silicon peak position and the silicon width across the measured area. First of all, if we look at the silicon peak position, we can see near the contact pads there's a downshift. This downshift corresponds to a stress of around 0.14 gigapascals. We can also see there's a reduction in width. We can see this downshift and reduction of width typically continue from the contacts in the same regions we saw in the photocurrent image. So we can see I've again put a square around the region where this bad or different region is coming further out from the contact pads. In addition, on this image, we can see a lot of circular features. The cause of these features is unknown, but we're basically seeing a slight upshift in position and also again a decrease in the width. So we're expecting these to be better quality silicon regions, and the cause for this is currently unknown. Now we can bring the two data sets together. Immediately we can see there's a clear correlation between the Raman and the photocurrent data. So we've got perfect overlay with the contact pads, for example, and we can also see the region of low photocurrent adjacent to the contact pads is duplicated on the Raman peak width image. So these regions have a lower peak width. We looked into this a little bit further, and one of the fabrication steps for these PERC type solar cells is a selective emitter process. And for this, they heavily dope the regions under the finger with phosphorus to reduce the contact resistance, whereas they only lightly dope between the fingers, and they do this to minimize the recombination losses. So what we're actually seeing is the region where the contact pads is with the heavy doping is too large for the contact pads. So this is probably a production or processing error where they're basically putting on too big a heavy doping region. So we see this really poor recombination region. This is in strong agreement with the Raman results. So literature data where heavy phosphorus doping has been done to silicon shows a decrease in the silicon peak width and causes a downshift in the silicon peak position, exactly as we've seen in this case. So we can be reasonably certain this is the case. And ultimately, if we want to determine if this is the performance issue we're seeing, we then need to run another batch of solar cells to basically determine if that is the limiting step. So that's the regions adjacent to the contacts, but what are these circular defects doing and what effect have they got? So we see lots of them all over the sample, and I'm able to easily again correlate them between the photocurrent and the Raman. So in this case, these circle regions show an increase in photocurrent. They also show a slight upshift in the Raman peak position and a downshift in the width, indicating that they're basically better quality crystals. These regions seem to be grouped, and we seem to have a trend where they run in streaks, running from, in this case, from the top right of the image to the bottom left. Although we're not able to pin down the cause at the moment, this is an interesting finding because it tells us that we have these better crystalline regions in the wafer, and it will be good to determine why, because it's a quality control issue if this occurs more often. To summarise, photocurrent measurements allowed variations and defects in single crystalline silicon single cell mini modules to be detected quickly. By doing simultaneous Raman measurements and photocurrent measurements, it enabled us to better understand the cause of the photocurrent reduction and enabled this issue to be correlated to the fabrication process. And really the big take home from this piece of work was that the selective emitter process was believed to be much more accurate than has been demonstrated here. So ultimately the manufacturer needs to go back, evaluate this fabrication step and determine if the higher level of accuracy is required. This might be the cause of the significant loss of cell efficiency. The final case study I'd like to talk about today is characterization of perovskite materials and modules. As discussed previously, Raman spectroscopy is an excellent tool for chemical identification, but it also provides vibrational and electronic information. And for this work on perovskites, I'm going to focus on methyl ammonia lead iodide. This material, MAPI, is unstable under ambient conditions. What I want to highlight here is that Raman can easily detect the degradation products of MAPI, which is lead iodide. This allows device stability to investigate it. Here we've exposed a MAPI film to a 532 nanometer laser for 5 minutes at high power density. The spectra are shown on the right hand side, and what you can see, there's no instant degradations, the sample's not being oxidized or burning, but over time you can see a build up of the peaks at around 110 and 96 wave numbers, and these peaks correspond to lead iodide, the breakdown product. And what I really want to highlight here is how easy it is for us to identify that product, because it's useful for looking at these types of cells. Now I want to show a few more detailed examples, and all these examples were carried out in conjunction with Specific at Swansea University, and the work was carried out by Harry Lekhani, supervised by Jeremy Barbe and Dr. Chung Soy. And Harry was one of our sponsored students, and he did a lot of this work, and it's very interesting and it's been published. So I'll give you some examples and you can always check out the papers later. So my first example continues on the monitoring degradation theme. So this slide has lots of images on, and these are map images showing the photodegradation effects of applying a solar simulator to an inverted architecture planar perovskite device. And in this case, we've taken 200 by 160 micron maps using different characterization methods. So we've done PL, photocurrent, electroluminescence, and also we've done Raman, and the details are shown across the top. For these measurements, the pixels on the perovskite device were partially shielded using a TM grid, and this enables us to get contrast on the image, and also enables us to probe any changes in PL, photocurrent, electroluminescence or Raman between degraded and undegraded regions in the same map. And I should note that these images are taken at different time intervals from different pixels. A quick summary of the data. So if we look at 0 hours, we basically have our bench line, and we can see after an hour, the data is generally quite similar. Photocurrent values are very similar, and we're not seeing any noticeable artifacts in the images. Around 2 hours, similar sort of situation. However, once we get to 3 hours, we see brighter regions in the PL where the sample has been exposed to the sunlight and partially degraded. And we also start to see these features start to appear in the PL position image. However, at this point, the actual photocurrent remains reasonably constant with what we've seen before. So these ones, first four, are pretty much running on the same scale, and you can see that there might be some differences from pixel to pixel, but they're all roughly the same. That we start to begin to see features with lower photocurrent, where we're seeing the regions with higher PL intensity, obviously related to the fact that in regions where we have better radiative recombination, we have lower photocurrent regions. As we go to 4 hours, the TM grid becomes very apparent on this pixel. So you can see basically we have the regions covered by the TM grid have pretty much standard PL intensity, and the other regions have a much higher intensity, more than an order of magnitude higher. We see some effect in the PL position as well. So you can see a slight downshift in the PL band center, and we can see immediately we've got a reduction in photocurrent. So whereas all the others have been sort of like about 2 × 10 to the -8 amperes, we're now down at about 1.5 or 1.6 × 10 to the -8 amperes. And as we go on to 5 hours, the effects worsen. So in this case, the PL image is not so clear, but we can definitely see PL position shift, and we can see that in the photocurrent region as well. And it now is very clear where the grid lies and where it doesn't. And we see quite a significant reduction of photocurrent compared to where we started. Now, a couple of interesting things about this. So first of all, we have a Raman measurement throughout looking for lead iodide being a degradation product. And what we don't see in any of these measurements is any lead iodide production. So this is more like a burn-in effect, where basically we're seeing slow continual degradation, which is probably affecting the crystal structure of the mapping, not affecting its chemical state. But obviously this is quite important because we now have a finished module, and we're able to show that the photocurrent we're getting from this module is reduced even if we put it in a solar simulator for a small amount of time. And this doesn't bode well for this type of module being exposed to daylight and being used for a long period as a solar cell, and we will definitely see some reduction in peak efficiency over its lifetime. My next example is just highlighting the presence of this lead iodide degradation product. So here we're looking at a large area. So we've looked at a module which is about 7 by 6.5 centimeters. We've scanned across the module using Streamline to do very fast mapping. And here we're just looking for the presence of lead iodide, and we can find it in the module. And we kind of see these arc shaped features, probably due to the coffee ring effect in the production of the module. The case here is probably that the lead iodide, which builds up at the outside of the ring, is more dense, so it's not completely converted to MAPI in the fabrication step. And this just kind of highlights that this sort of characterization is important when scaling up processing methods, because although this method may have been quite successful for very small scale films, as you go to large scale films for module size, the recipes need to be tweaked to ensure best production quality and performance. My next example is looking at comparing different deposition techniques. Mesoscopic perovskite solar cells have emerged as one of the most promising perovskite solar cell architectures. It's nice because it's an all printable triple mesoscopic stack. However, it's still lagging behind other types of perovskite solar cells in terms of efficiency. So around 16% to state of the art, which is about 23%. However, the key benefit here is these cells are very stable. It's being very easy to make. And the way these cells are made is perovskite precursor solutions are infiltrated into the mesoporous triple stack. And here we're comparing a 1-step and 2-step deposition process. We're looking at spatially correlated photoluminescence, photocurrent, electroluminescence, and Raman maps to basically provide a detailed understanding of the different infiltration mechanisms and determine what the electronic contacts at the interfaces and the local photosensor for the cells are. As I said, this work was conducted at Specific in Swansea and has been published, and I've put a link to the paper at the bottom of the page so you can go if you're interested and have a look. On this slide, I've just shown some examples of the combined method. So here We're just focused on a defect that was seen in the two-step process, and by combining the PL, photoluminescence, EL and Raman, we're able to identify what's going on with the defect. So here we can basically see we have a region where we have much higher photocurrent, we have much lower PL intensity, and we have much broader PL intensity. So typically a lower PL intensity and higher photocurrent go hand in hand because it implies the sample is more efficient at charge transfer, so it has a lower radiative recombination. From the Raman, we can see that the actual defect in the center of this region is primarily TiO2, which is one of the materials used for the mesoscopic stack. So we can basically see this is a region where we just have a high concentration of TiO2 for some reason, and as a result we've got different electronic effects compared to the bulk perovskite material. So now I want to show you data taken from a much larger region of the one-step MAPI film. So this is a non-uniform film. From the figures we can immediately jump to a few conclusions. So we've got micrometer sized dark circular features, which we can see in the optical image, and we have good spatial correlation of these features with all the techniques. So we can see in the PL, for instance, we have lower emission in these regions, and we have a peak position upshift, and we also can see that they're actually a bit sharper as well in places, but also sometimes broader. One of the interesting things again is we have an increase in photocurrent, and that corresponds directly with the reduction in PL intensity, again related to radiative recombination. This suggests there is better charge extraction. Probably the circumstances there is better electrical conductivity between the perovskite and the underlying mesophorous titanium dioxide in these regions. However, the non-uniformity across the cell is quite undesirable. So now I want to go on and look at the two-stage process. And so I've got the two-step process here compared directly to the one-step process. And you can see the two-step process immediately has a huge number of benefits. So the first thing is these dark regions are gone and we now have a much more uniform surface. You can see that from the optical image we kind of have these white regions, or sort of and the actual formation of these regions is relatively complicated because basically what we're doing is putting two lots of lead iodide through the cell, and as a result the actual formation process is actually quite complex. But the key benefit with this two-step process is you can see with the one step we were getting photocurrents on the order of 7 times 10 to the minus 8. Now we're getting photocurrents on the order of 2 or 3 times 10 to the minus 7. So we're seeing a doubling in the photocurrent by using this technique throughout the whole cell. We also see, generally, if we're looking at these images, a much higher level of uniformity. But we need to be aware because there are some differences. So we are generally seeing, for instance, an upshift in the PL peak position, which obviously affects how good the cell is absorbing sunlight. We also see a significant reduction in the PL full width half maximum. So basically, we now have what we describe as a uniform cell, whereas before with the one-step process, we had a very heterogeneous cell. So what I want to show you here really is by combining Raman with PL, with the electroluminescence, with photocurrent, we're able to do a lot more with these samples and learn a lot more information about them. And we're able to basically do some cause and effect type analysis and do good science. To summarize, here we have highlighted how Raman can be used to investigate perovskite solar cells at all stages, from raw materials to fully packaged modules. Renishaw's via Raman microscope can be used to conduct not just Raman, but also spatially correlated photocurrent, photoluminescence, and electroluminescence measurements on these types of samples, which is obviously interesting for getting better data. And combining all these analysis techniques on one system allows for a greater understanding of the underlying structure, electronic properties of these materials, and being able to correlate the two, enabling better, more comprehensive scientific research. So to conclude, in this talk we have highlighted how Raman spectroscopy can be applied to green energy research. We've demonstrated the power and flexibility of INVIA and its ability to cover all these different fields. We've illustrated how Raman spectroscopy used in conjunction with other measurements such as photocurrent, electroluminescence, PL, or live track to get topography information allows better scientific understanding of your samples and hence helps you with your research. My hope is that we have shown you some good science today, which may stimulate your future work and may make you think about things you can do with your samples or in your research area. So with that, I'd like to thank you and go on to questions.
Thank you, Tim and Tim. Let's now answer some questions. Attendees, please keep typing your questions into the chat window. If we don't have time to cover them all today, we will respond to you by email. Now, on to the questions.
Thanks, Ian. So we've got a whole range of questions here. The first question I'm actually going to combine into two because it's really on a very similar topic. So it's really about how you can use Raman to measure stress and how you go about doing that process. And then also, how many wave number shift would you say is significant and not within error of the measurement itself?
All right, so that's quite an interesting question. So one of the properties that Raman measures is obviously measures the vibrations in crystals. And the energy of those vibrations depends on the crystal structure, so the shape, whether it's cubic or hexagonal, and that will give you very specific Raman modes for that structure. But it also depends on the interatomic spacing. So as you start to drag the atoms further away, you change the energy. And from that, we can directly correlate the energy change with strain in the material. And you can go back and then use that to work out stress if you know the Young's modulus of the material. And there's something called the deformation potentials, which are normally published in papers and literature, which tell you roughly how much Raman shift corresponds to a given amount of strain or stress in a material. Now, with our systems, they have a very high spectral resolution. So you're able to really accurately measure the position of the Raman mode. So on these sort of systems, if you're measuring silicon, we're able to accurately determine the peak center to probably better than 0.01 wave numbers. So this lets you measure phenomenally low levels of stress and strain. What is actually relevant though in terms of this? So for a typical material, say silicon, you might see a 3 wave number shift as a result of 1 gigapascal of stress. So most of the time we're looking at sort of below 1 wave number shift. So you might be seeing 100 or 200 megapascals of stress at the most. And generally I wouldn't worry about it if it goes below a 0.1 wave number shift or something like that. But it gives you an idea of how you can really measure the stress and strain. And this is useful in a large area of applications, not just in semiconductors or green energy, but we use it to measure 2D materials. We use it to measure coatings, all sorts of things where stress and strain are really important in any sort of material science problem, really.
Okay, thanks. That's a nice detailed answer. So we've got another question here about measuring the thickness of layers. Could you talk a little bit about how you go through that process? Okay,
so it is possible to measure layer thickness with Raman, but there are a couple of requirements. So the first thing is that the layer needs to be transparent to your laser excitation. Obviously, if it's not, you only measure the surface of the material. You don't actually know how thick the layer is at all. You don't probe the whole layer. The other thing that's required is you need to have quite good quality materials, and you need to basically do a calibration measurement. So we sometimes do this with protective coatings, with polymers, other sorts of materials, where we'll take materials of a known thickness, run them measurements of them, and accurately determine how much Raman intensity we get for a given layer thickness. And then we can use that to basically generate an empirical fit. So we can then say, okay, I'm measuring this unknown. It has a Raman intensity of X. As a result, I know it's 5 microns thick or 100 nanometers thick. And we can just do that directly for empirical correlations.
Okay, thanks for that. And then there's another one here. Can Renishaw provide some reference Raman spectra for the lithium-ion battery materials? Also, any information on Raman measurement conditions for battery materials would be really helpful.
Okay, so in this work, there are a few different sets of measurements. They're all taken using green laser excitation, predominantly 532 nanometers, although I believe the one on the in-situ cells was done with 514 nanometers. And here, one of the real key things for lithium-ion batteries is that basically you keep the laser power low, because with excess laser power on the surface, you'll basically damage the batteries and you'll cause transformation of products. So I think here we're looking at less than a milliwatt instant laser power on the surface during any measurements. Measurement times are typically quick. So for some of the mapping measurements, we were looking around half a second. I think for some of the single spectrum measurements, it was a bit longer because obviously we want to spend a bit more time getting a really good reference. We do have quite a good selection of references for the different materials. And I guess if you contact the apps team, we could probably provide you with some of those, or at least I know that we have an application note which has like quite a detailed figure in it, which has spectra from multiple materials. So that's a good starting point at least. But with all these things, lithium-ion batteries are now quite heavily studied. So in literature, there are just plenty of resources to actually identify all these different materials.
Okay, great. And then we got a question here, a relatively basic question about what's the effective spectral resolution of an INVIA?
Okay, so the spectral resolution of INVIA, if you're talking about the actual resolution, can be better than one wave number. It depends a little bit on the configuration. So INVIA is a very modular system, and you can basically choose to have very high resolution gratings to get really good spectral resolution, or you can choose to get lower resolution gratings to basically have a bigger spectral range. And it just depends on your needs, really. Generally, though, one general comment is that most Raman bands at room temperature have a natural line width on the order of 3 or 4 wave numbers minimum. So as a result, there's not a huge benefit of going to very, very high spectral resolution. The other comment is that the spectral resolution should not be confused with the spectral shift resolution. So our ability to determine a band center is much, much better than one wave number, as I mentioned before, around 0.01. What spectral resolution represents is our ability to separate 2 convolved bands, and that gives the limiting factor of how close together the bands can be before we see them as a single band or not.
Okay, and I think that a typical application and instrument would generally have a 1 wave number spectral resolution. You know, I'd probably say that that's pretty typical for most applications, and a higher resolution than that is probably quite niche. But of course, you know, because it's such a flexible system, we can go to lower resolution gratings as well. So, you know, there's a whole range of things there. Okay, and there's another quite general question here about the difference between FTIR and Raman spectroscopy, and of course they're quite complementary techniques. There's lots of different answers to this question, Tim, so I don't know if you want to keep it quite brief, but what are the main differences there between those techniques?
Sure. So let's talk about, I suppose, as we're talking about Raman today, let's talk about the complements of Raman over FTIR. So both give you information on the vibrational states of materials. So ultimately they can give you the same information, but in general they do not, and that's because they work better on different materials. So one of the strengths of Raman is it works on materials in any phase. It works on materials in water, which are challenging using FTIR. It also works without any sample preparation. So those are all great strengths. The key benefit of FTIR in reality is the fact that it's a much stronger effect than Raman, so measurement times tend to be shorter. So it's pros and cons depending on exactly the material and exactly what you want to do with it.
Sure. Okay, so there's quite a specific question here about how can the morphology, so the morphology of the sample surface, be pictured after a streamline mapping measurement in the examples you've presented here?
Okay, so I think quite a vague question, but I'll try and answer as best I can. So we have a couple of options. So with our systems, they're equipped with research-grade microscopes, so you can take optical images both before and after your measurements. The other thing is now with our new live track functionality, basically we use that to track the focus position, so the actual surface position of the sample during measurements. And as I showed, for example, in the first lithium-ion battery example, you can actually use that surface position to generate a 3D surface of the material. So as a result, you can look at the roughness, which obviously gives you another indication of the morphology of the material. And so that's a really nice and really useful effect, especially if you have samples which you want to measure the roughness of. Obviously, there are some limitations in that into what resolution you can achieve because it's an optical technique. It's never going to compete with AFM, for instance, for measuring morphology.
Okay, and I think we've got just time for a couple of more quick questions. So in stress analysis, can we measure the lattice mismatch?
Okay, so I presume here by lattice mismatch, you mean the mismatch between 2 different materials. And you can measure the strain of each material. So you should be able to measure the mismatch between them. So fundamentally, you should be able to measure from a strain-free material, if you have an example. and measure the Raman shift, and then you can basically measure your as-is material, which is, I presume, a material grown on some sort of substrate, so they have a lattice mismatch, and you then should be able to determine what the relative strain is for these sort of materials, and that can just be done using like an empirical calibration once you have the strain-free position.
Okay, and let's make this our final question. So for poly-semi-crystalline organic materials like small molecule conjugated dyes, they can stack in different domains. Would your mapping be able to differentiate different crystal orientations, like crystal pointing in different directions?
Yeah, so that's a really good question. So one of the things we can do with our systems is we can measure, we can do polarization Raman measurements. And this allows us to determine not only the crystal structure of the material, so the dye crystal structure, but it also allows us to determine the relative pointing of the crystal axes. So if you have different domains, it's slightly different orientations. So for an example in that presentation, I think if you looked at the silicon, one of the silicon examples, I showed different intensities of the silicon, or Tim presented that data, and that's related to just different crystal orientations of the same silicon structure. So we're able to do this with these domains. It can definitely be done. I've done it in conductive polymer materials before, so I think it should be viable for these sort of semi-crystalline organic materials, although you need to be a little bit careful on exactly which one. But yeah, I think it's fundamentally something that can be done.
Yeah, and I think that you can do the opposite as well. If you specifically don't want the orientation of a crystal to impact your Raman data, you can think about circularly polarizing the light, essentially depolarizing that to remove that effect. So there's quite a lot of control you've got there over how you kind of manage that process depending on the type of work you do. But thanks for those answers, Tim. Let's pass back to Ian.
Thank you, Tim, and thank you, Tim. And thanks to you, the audience, for the questions. If you didn't get a chance to ask your question, you can still do so by
So I think we've lost audio there from Ian. So yeah, if you've got any other questions, then you can use the link there for Ask Raman Questions.
Found out really short.
And then I think Ian's audio is just chopping in and out. And then we look forward to our next webinar, which is going to be looking at Raman Spectroscopy, a vital tool in art and cultural heritage. And again, that'll be myself and Tim Batten on the 20th and 22nd of July, where we're going to be presenting a range of data, both on the Envia and on the Versa system, where we can do sort of more portable work. So it's a really exciting opportunities there for cultural heritage type applications.